Okay.
Okay. Okay, so welcome everybody. Hello again for those who have continued to following us, and welcome to the new listeners to this workshop, Statistics for Non-Mathematicians. Simple title, not so simple task to explain. Right. With us here today is our dear colleague, Dr. Pero Hrabač from School of Medicine here in Zagreb, who has many interests and has runs 2 departments there, right? You are head of a medical informatics, statistics,
department of the informatics,
informatics and all that.
Yeah, the other one.
I'm obviously not very good at that. So the floor is yours. I'll give it to you straight away. Show us, please, what we can do with statistics.
Thank you.
Better. Thanks.
Thank you, Zenka. So thank you once more for the introduction. And let me just share the screen. Now, please don't get scared. I'll just show you how does the course normally look like. So this is the introduction to statistics for non-mathematicians, and as you can see, the normal this is what I usually do. It's 340 slides, but don't be afraid. Today we'll keep it just short and sweet, and I'll try just to convey to you, to discuss with you some basic principles. And let me just share the first screen so we can start. Okay, share screen. Share. Okay. Can you see my PowerPoint? It
yes.
Should be. Yeah.
Yes,
thank
it's
you.
okay. Yeah.
Okay. So it's cases in statistics. It's statistics for non-mathematicians. Why cases in statistics? Because quite a few people called me during the last few days asking what are you going to talk about. So I said I want to go through some, I don't know, less well-known examples, how the statistics can be used and misused and so on. And the basic feedback I got was, well, that's all well and nice, but what we would like you to just go through the basic introduction, through the basic concepts, and just to once more go through all of this, because statistics was the course in statistics was long ago and we forgot almost everything. So today, what I'll try to do, I'll try to keep it short, so under 1.5 hours. I'll try to show you some basic concepts. I'll try to show you some basic errors that people do when managing data. And in the first part especially, I'll just go step by step and really cover the basics. So if you have any significant training in the field of statistics, if you yourself also hold any kind of education, I think that this will be a waste of time for you, and I think that you'll spend your time better drinking coffee or something like that. But of course, I'd be flattered if you stay along. For all the other of you who are interested really in basics, as it was suggested to me, then please stay here and see how you like it, and I hope I won't bore you too much. So my name is Pero Hrabač. I come from Andrija Štampar School of Public Health, and the department I come from is the department with the insanely long name. It's a Department of Medical Statistics, Medical Informatics, and Epidemiology. So this is the department with, I think, the longest name on the faculty. I'm an assistant there. I also run at this moment Department of Informatics at the School of Medicine. So I'll try to combine the experiences from these two jobs. Also, my background before I came here to the School of Medicine is in pharmaceutical industry. For almost 15 years, I worked first of all for the small pharma and then for the big bad pharma, doing statistical reports, statistical analysis for clinical trials, and so on. So this is my basic background, and this is, let's say this should be my qualification to hold courses, workshops like this. So what's the goal? What's normally the goals of such let's say introductory classes or workshops? I know this looks terrible to you, especially if you're new to statistics, but the idea that we have on day one is that by day 3, possibly, we would like our attendees to understand what this means, what this graph, what this figure means, and how you can use it in your research, how you can use it with your data, and what can you do with this. Now, what we want to teach you, what we try to teach you during the normal course, which is 3 days, if we have a course, if we have on our department, we take 3 weeks for our students to go through all of these topics. So let's say between 3 days and 3 weeks, we want our attendees to understand, to finish the course understanding what this means. So what can we do in hour and a half or 2 hours? Not so much, but we can cover some basic aspects of this. So what's in the picture? What's this figure represents actually is you could say the way of statistical thinking, the way that you can draw conclusions out of your real world data. So you've got your Excel sheets, you've got your experiment data, and the question is, okay, I want to use statistics to generate new knowledge, to conclude something, and how do I do it? Well, this is the basic outline. How do you do it? This is how you choose the statistical test. We'll get back to statistical tests later, but just this is one of the steps, and in the end, it would be great if you could have a bit better understanding of what this figure represents. So this is the most complex one. The same figure, basically the same figure, can be much more. It can be simpler, as you can see. It can most of the information that you have here is shown here as well, but it's not in such a complicated way, and you can make it even less complicated, of course, by discussing only a few tests. So if I want to cover most of the tests that you normally need, of course, you know that there are hundreds and hundreds of statistical tests and approaches to statistical thinking and approaching to testing hypotheses. But if I want to cover most of the questions that will arise in doing anything in analyzing my data, this is what I need. If I want to simpler version, then this is it. If I want completely stripped down version with only the bare basics, then this is it here. But you actually can't believe how much you can do with only these 4 tests, with only these 4 approaches to testing and to statistical thinking and data analysis. Now, additional 2 tables, you don't have to pay special attention. It is just to show you that the same thing can be shown in many different ways. So it can be in form of a graph, it can be simpler, even simpler, it can be more complicated, as a table, less complicated as a table, but basically you always have the same tests for the same combinations, for the same data combination, and for the same approach in data analysis. The point is that you are able to understand what this means, and the way the data are displayed are actually secondary. So these are the ideal goals. We take 3 days or 3 weeks or whatever to give an introduction to all those methods. Today, since we have quite a little window of time to discuss a few of these topics, we'll have a much simpler approach. But I think it will be, I hope actually that it will be interesting for you. Now, this is the ad for the beauty product that I've seen in a in the shop window this summer. So I thought that it could be interesting for this course. Of course, when we are discussing ads or whatever, whichever form of customer satisfaction or whatever, it doesn't have to be beauty products. It can be cars or any kind of, I don't know, restaurants and so on. The point is, these people analyze data and they want to sell you something based on the data they have gathered. You actually want to do something comparable. You want to gather data, to analyze data, and to publish, to have a publication. They want to sell, you want to publish. However, the data behind this, the data gathering process and the data analysis process is actually the same. The goal may be different. So the goal for today, we'll start with this ad. So it could be any ad. It could be for Mercedes-Benz. It doesn't matter. The point is, what are these numbers? How do they come to these numbers? And what's the process? And what's the conclusion? And is this really so, or it isn't? So for those of you who who don't speak Croatian, so this is a skin product which guarantees 45% more luminosity, 41% more elasticity, and 0.3% less of thin lines on the skin, I presume. If you see the ad on the street, you'll see that in the small print here, you'll see, if you start to analyze it from the small print, which you should always do as a statistician, that there are quite a few things that you can worry about. But let's see the data set. The data set is not for this actual product. This is for the data set is for a similar product, because my friend who is a lawyer warned me that if I show the data set for this product, which is actually available, they can sue me. So I'll show you data set for another product, but you'll see the point. So the ad claiming something based on the gathered data and on some kind of data analysis. So I'll stop sharing the screen now, and I'll share with you in the chat a link. Just give me a second, to the data set. So since this is a workshop, the idea is that you use your, the only thing you need is Excel and access to the internet. You obviously have the access to the internet, so this shouldn't be a problem, and any version of Microsoft Access will suffice. So I think from 97 onwards, everything should work. So I'll just upload a file for you now and share a screen, share a link with you now. Just give me a second. Of course, if you've got, if you have any problems in accessing or analyzing, just raise a hand and I'll try to answer. Okay, so this is the link in a second. So you've got the link to all panelists and attendees. So there is a link to file in your chat. So if you would like to have a real hands-on experience with the very basic but still data analysis, we'll do some statistical tests later. If you're going to have a hands-on experience, please just download the Excel file, and we can start the analysis. I'll open now the Excel file myself, so I can share it with you. So the name of the file name is face screen, and this is how the data set looks like. So you'll see that it's actually quite simple, nothing special here. So I've got some ID and two set of scores. Now, what does it all mean? We'll see later if we have time. We'll analyze much more complicated data set, and then you'll see how important this is. It is to code your variables adequately. So these are the contents. You should see my PowerPoint now. So this is dataset 1. The name of the dataset is face screen, and as you can see, you've got contents variables of the in the dataset. We've got only 3 variables. So ID is number of the participant. It could also be name and surname, but of course it needs to be anonymous. Score is satisfaction with the product from 1 to 5. 1 being completely unsatisfactory and 5 being excellent. Verum is a product that we are testing, so it's this column here. So this is the Verum product, and control is a placebo formulation of the product, meaning that this is most likely the same thing, but without any active ingredients. So only actually 3 variables: ID, which we use to identify each of the persons or each of the participants; score 1 to 5, like in school; Verum and scores for Verum and placebo products. So let's see what we got here, and what kind of data do we have here. You'll see later why this is important. This is pretty basic, as I said before, but we just need to go through these things, because you would be surprised how many people actually forgot or didn't even have the concept of the types of data. So we've got 2 basic types of data. Any kind of data you have, any type of variable, can be of actually 2 kinds: quantitative and qualitative. So quantitative variables are these that I either count or measure. So discrete variables, integer, ones that I count, number of attendees at this workshop, and continuous, the ones that I measure. Age, I don't know, blood count, weight in kilos, and so on. Of course, weight in kilos, for example, can be a discrete variable if the scale you have only measures and rounds up to the first kilo. So you can have, I don't know, 85, 86, 87, 88, not because you have exactly that weight, but because the instrument you're using is rather blunt and gives you just that kind of data. However, if your instrument is a more precise one, then you'll get continuous variables. To make things a bit more complicated, discrete variables can have also in some situations, discrete variables can yield continuous results. If you, for example, if you have a blood pressure in RR, blood pressure, if this is a discrete variable because you have, for example, systolic blood pressure is 121, 125, 115, and so on. However, when you count, when you show means, medians, and other values derived from this variable, it can be continuous, because when you have a mean of 10 blood pressure assessments, it doesn't have to be discrete anymore. It can have one or more decimal places. So here's the difference. So quantitative and qualitative, and these are all the basically all variables must be in one of these two categories. Quantitative, I either measure or count, and qualitative, binary, nominal, and ordinal. Here are some examples. So binary, yes, no, female, male, dead, alive, and so on. Binary variables with only two possible values, and there cannot be a third one. Nominal, like colors, now you get additional information. So you don't get information which is binary. For example, car is either black or not black. You know the famous saying of Henry Ford at the beginning of 20th century, that you can get a car in any color that you like as long as this color is black. So if you wanted information if the car is black or not black, this is binary. However, if you want to know if the car is black, red, white, green, or something else, then this is nominal. And you can get basic information with yes, no, additional information if you code this variable as a nominal, and even more information if you use ordinal variables. You'll see why. So this is quite simply. So the nominal variables, you have categories. Ordinal variables, you can rank those categories. Interval and ratio, we'll mention this later. You have equal spacing. What does this mean to have the equal spacing? Here, for example, equal spacing means that if you measure age, then 1 year is always 1 year. Difference between 101 and 102 years of age is the same as between 5 and 6 years of age. Kilo is always a kilo, and a centimeter is always a centimeter, and a mile is always a mile. So this is what it means. There is equal spacing. Now, what's the difference between interval and ratio variables is there is a true zero. You don't need this distinction too often. However, it's useful to know. Ratio variables are those who have true zeros. So, for example, distance, there is a true zero. So distance of 0 kilometers, 0 miles between me and someone else means that we are at the same place. However, distance of 1 mile, 2 miles, and so on means that we are so and so much apart. However, if you measure a temperature in the degrees Celsius or Fahrenheit or whatever, there is no true zero. There is zero, but this zero doesn't mean absence of temperature, but just means that we made a agreement that the temperature that water freezes at is zero. But this doesn't mean that there is no temperature at for this exact value of this variable. So let's go back to the Excel file, and in the Excel file you'll see that we have one nominal variable, which is ID. So this nominal variable could also be name and family name, or number, or whatever. So these are categories. As you can see, we have 42 participants, 42 people who have tried the product. and we have a score for two groups of people, of participants. Now, the first group, they got the product that is advertised, and the second group got the control, the placebo, probably the same thing, but without the active ingredient. And now, the basic thing you can do, you can see the values here, and probably if I ask you what's the first thing you would do with this? Okay, we can calculate the mean value for score in first group, in the second group, and see which one is better. So it seems plausible. So we can do it. We can do it here in Excel. I'll write my results here. So I'll just bold this entire column. So let's say that I want mean for verum and mean for control or placebo. I'll use a function. So the function, as you know, the name of the function is average. And I'll just calculate the average of verum. Okay. And then the average, the same thing for placebo, and I'll get the same number. Why? Because I need to increase the number of decimal places. So I can increase the number of decimal places, and you'll see that I got means for both groups. So if I can just select this, insert recommended charts. Excel is so kind that it recommends me the chart that suits this purpose the most. However, if you have the older version of Excel, then you do the same thing. You don't have the recommended charts, but you have it here under columns. So you can select 2D column, you get the same thing. For those of you who have the newer version of Excel, recommended charts, okay. And yay, this is what we wanted. So let me just increase the font for a bit so you can see it better. So I've got two groups. Mind you, these are the real data, not for the product you've seen, but for the other one. So you've got two groups, and you see that in this group, in verum group, the satisfaction with the product is much higher. So, I mean, it's clearly visible. However, you don't have to look very carefully to see the major problem with this chart. So the Excel actually, it seems wants to help you a bit with the cheating with your results. So you see the vertical axis. You see that it doesn't begin at 0 where it should, but it begins at 2.4. Why? Because this is the way you can better show the differences between the groups. I can increase this to even 2.6, and then I'll get even more pronounced the differences between group. However, how it should look like is this. Now, when it looks like this, it's not so obvious anymore. I mean, this is better, but it's far from this, you'll agree. So let's stay here, and we've done the basic things. We've displayed the mean values, of the customer satisfaction for one product and for the other. So okay, let's go. Let's see what kind of statistics should we do with this data we have. So the first thing we should do, the first thing you always do, you do the descriptive statistics. So you just you use two things: ups, back, central tendency, which is mean, for example, and measures of dispersion. So you've got measure of central tendency, which is mean or median. We just calculated the mean in Microsoft Excel. And then I need some kind of measure of dispersion. Why do I need a measure of dispersion? Because mean alone doesn't tell me that much about how does the distribution of my data actually looks like. So what we want to do, we want to show means, difference in percentage, medians, and some kind of chart. We've already done that. So what should we show? Should it be means or medians or something else, and why? What we want to do, we want to describe the data. We want to describe the data using basic or descriptive statistics without concluding anything definitely. But we want to describe the data using both measures of central tendency. So how does the mean average looks like, and dispersion, which is standard deviation or interquartile change. So let's briefly discuss the additional information, the additional data we need to show here. So we give a better description. We give a more throughout description of the data we have. So this is the definition of standard deviation. So this is average amount by which score is different from the mean. So why do we need this? So here's an example. I'll go back to Excel now to show you. Okay, Excel, new window, share screen. Okay, so I've got two groups. Of course, you're welcome to do it with me. And I've got monthly salary in let's say thousands of dollars or something like that. In the first group, okay, I can also have some ID. So person 1, 2, 3, 4, 5. In group 1, these are the salaries: $5, $6, $7, $8, and $9,000 per month. And in group 2, I've got 1, 4, 7, 10, and 13. So what can we do? We can count, we can calculate mean, we can calculate median. We'll discuss median in a minute, and see what we get. So average, okay, when I copy it here, I get the average for here, and median. So I've got quite a few functions. I've got actually 4 functions that will that give me the value for median, but let's use the simplest one. So the median, and it's the same. And here, it's not the question of number of decimal places. Both, as you can see, both groups have same number of people, same mean, same means, identical means, and identical medians. What saves me here is standard deviation. And now you'll see what we get here. So function, this is the function. Standard deviation, if you've got an older version of Microsoft Excel, there are the name of the function can be a bit different. So you see, it says std evp, and this function is available for compatibility with the Excel 2007. So you can, in older version of Excel, you have exactly the same function, but with a different name. So I'll use this one, standard deviation, and I'll calculate standard deviation of this group here, and then just copy paste it here and decrease the number of decimal places. Okay, let's go back to the PowerPoint, and let's just remind ourselves. So the standard deviation is the average amount by which scores differ from the mean. So the information that standard deviation gives me is exactly that. So you can see here in this sample, for which you can see, of course, it's easy to notice such things when you have five measurements, five people, five participants. But imagine you have 300 or 5,000, then it's not so simple. So here, as you can see, we've got standard deviation of 1.58, and here we have a standard deviation of 4.74. So these data, means and medians, these don't actually give me any information about dispersion of this data here, of these values. However, standard deviation gives me quite a useful info how this and this people salaries in this case. Imagine that this is department A and department B with exactly the same mean and median salaries, but with drastically different standard deviations. So the standard deviation is the information, the additional information you need to describe your data, so you get much better picture what is going on actually here. So let's do this standard deviation in this here sample. Okay, so we'll do standard deviation for verum and standard deviation for control. We know the formula now. It's stdiv.s. So the first one, and for the second one, stdiv.s, you just select column, and this is what we get. So we get, now we've got a bit more info about the data in our data set. We see that you can see that there are differences between these two products, and the standard deviations are approximately comparable to the means of the values we found here. So, okay, now you can claim that your product is superior to placebo. Why? Because satisfaction of the people who bought or who were given the product was higher than the satisfaction of people in group 2. However, the question is, how can you decide what to do with this? So we'll go just through the few slides, and I'll just let me just find. Okay, we can continue here as well. But the point is this: if you want to, let me get back just to Microsoft Excel. You can see the means, and you can conclude this is the higher mean is better because 5 is higher than 1. However, what you also want to conclude are these means result of some kind of pure chance. So what's the probability actually that the differences between those two treatments are just the consequence of a chance? And how can statistics help me with this? What can I do? What can I do? What can I do to get the answer to these questions? Are these differences just by chance, or is there something beneath this. If there is something beneath these differences, between this and this, I suppose it will be the treatment. If I have selected the sample correctly. So if these two groups, so the group that received verum and the group that received the control treatment, if two groups are exactly the same, or just comparable in terms of age, of gender, of I don't know, number of times per day the product was used, and so on and so on. If these two groups are comparable, basically in all the parameters except the one that I want to test, which is verum versus control, if these two groups are comparable, then I can conclude that there is a difference. What I want to know is this difference actually, is this a real difference that I can also expect in general population when I use my product on thousands of people, or is this just a consequence of a chance? So to get the answer to this, we will have to discuss an additional complex, which is a distribution, as I promised in my in the materials. So why the distribution? Because the distribution of your data basically allows you to select the statistical test that will give you an answer to the question. So you will have the question. In our case, the question is which product is better. You want to select the statistic test to give you the answer. Product A is better, product B is better, and is this a consequence of a pure chance or not? And you want to be able to select the adequate test. Test selecting is the thing we've shown in the beginning. So any selection of tests, statistical tests in statistics begins with this. Can you use a parametric or non-parametric test? The kind of test, the type of tests you will use so you get the answer to your research question depends on how your data are distributed. So are your data distributed like this? So this is classical examples. This is a height in women and height in men. So you can see that most women group, this is the number of participants in the study. So you'll see that most women group around the central measure, around the mean, that you've got a very low number of women with extremely low height and very low number of women with extremely who are actually very high. For men, the thing is basically the same, only values are shifted to the right because men are on average are men are a bit higher than women. So you've got a mean at around 178 with just small proportions of men above 2 meters or very of lower stature. So the same thing for the intelligence. Most of us are around here. Some people are very intelligent, some people are less intelligent, but you can see that you see this normal Gaussian distribution in the population, and this is actually a very important feature of each piece of data you want to analyze. Now, what we have in our data set, we have some scores, and what we want to know, do our scores follow such a distribution? Is this even possible for our scores or not? Do our scores follow such a distribution or not? Because if they follow distribution like this, then we say that data are normally distributed, and then we can use this set of tests. And if that data are not normally distributed, then we can use this set of tests. So we will end up using either this or this here. In this table, the first one in this figure that you see here, the same thing is here. So you just choose the adequate parametric or non-parametric test depending on the distribution of data. Now, what does this mean? This means that we want to see if these values here and these values here, when we count them, do they look something like this here, or God forbid they look something like this, or there is a or something like this. So this is ideal. This is what we would like. This is what mostly corresponds to this one. But our data can also look very differently, as you can see. So ideally, we can have this. In our sample, we can have only people or mostly people with high scores and no people or much lower number of people with lower scores, or vice versa. We can have many people with lower scores and just a few people with higher scores. So the first thing in data analysis, you want to see if your data, when you group them, when you count your data, do your data follow distribution like this? Do they look like this, or do they look like any of these other possibilities? So let's see. I'll go back to Excel. In Microsoft Excel, I don't know if, not the easiest way, but straightforward way, because we have scores from 1 to 5. So we can see the scores for one, 2, 3, 4, and 5 for Verum, and the same thing we can see for control. We'll do it in a second. So for Verum and for control, we want to see the distribution. We can also see the distribution for both Verum and control, and then later see by group, or we can do it like this. So we'll use COUNTIF. So COUNTIF, this is the range. I'll fix the range with the dollar signs. So it will always look on the same range, and I want to know how many ones do I have here. And Excel says you have 8 occurrences of score 1. Okay. Then I want to change it and see how many occurrences of grade 2, 3, 4, and 5 I have. I can also sum it all up, and I can calculate the proportions. So I get so it's divided by 42 and times 100. So I get multiplied by 100. So I get the percentage. Okay. So I have the percentages, and now we do the same thing for the second group. This is boring and trivial, I know, but this is necessary so we can see how the data are distributed. So this is again the same thing. Here I change it to 2, 3, 4, 5, and I can also calculate the proportions. It's again 42 of those as well. And you'll see that the proportions are similar, but not quite the same. The final number, of course, is in the end is 42. What can I do with this now? I can again insert a graph, a chart. So this for Verum. I can also insert the chart for distribution of control. Distribution of control. So I've got these two graphs, and you can see that this could look a bit like this here. So this could resemble a normal distribution up to a point, but the other one not so much. Not really. Of course, we don't want to guess if the distribution is normal or not normal. What we want to do, we want to test it. We want to see. We want the software to give us the information if the distribution is normal. So why is this important? Again, if the distribution of our data is normal, if our data resemble such a bell curve when we draw a distribution, then we can use one set of tests, which is called that are called parametric tests. And in case the data are not normally distributed, then we use non-parametric tests. This is why it's important, and they can give quite a different results. Okay, so let's see how we can see if the data are normally distributed or not. If you have some kind of statistical software, so SPSS, Statistica, Stata, whatever, you have 101 options, of course, to see the distribution, to test the distribution of data, but you can also do it for free. So in my PowerPoint, I've got just a second. Share. Okay. There is a link, so you actually don't have to have any kind of software to be able to test the normality of your data. You can use any of these two links. The second one is rather rudimentary, but it gives you just a really straight answer. So I'll use the second one, and this is how it looks like. So again, I want to test if my data follow the normal distribution or not, so I can decide which kind of statistical test I'm going to use. So I'll go back to Excel. I'll copy paste all of my data here. So you do it just by pasting. I'll paste both groups, one above the other, and when I click on calculate, too many data points, okay, more than 50. Let's just do it for each group separately. Second. So this is what I meant when I said it gives you a straightforward answer. Your data is not normally distributed. So there is a p-value. We'll discuss the p-value later. But the point is the data is not normally distributed. I can repeat the same thing for the second group. Paste. I get the same results. So although it seemed here that this group is more likely to have normally distributed data, it is really not so, because we've tested the normality of distribution, and the software, the freely available software on the internet, it's this one. Just I'll copy paste a link for you in the chat. Just give me a second. So it's this one here, if you want to try it. I want to use this software or something like this to test the normality of the distribution. So what I got now, for the time being, I have mean values, which suggest that verum is superior to control. But I also have the information that data we have are not normally distributed. So when we proceed to the next step, which is asking our statistical software, can this be just a coincidence, or is this really so? Can we expect the same results when we give the product to hundreds and thousands of customers? We will know what kind of tests we need to use. Okay, let's go back to my PowerPoint presentation. So this is the normal distribution, which decides distribution of data, decides what kind of statistical tests we are going to use. Besides the statistical tests we are going to use, distribution of data is very important in the statistic, the exact statistic you're going to report. So by exact statistic, I mean, do you want to report mean and standard deviation, as we discussed earlier, or you want to report interquartile range and median? Now, what's the difference? The difference is actually quite important. Why? Because depending on the type of the distribution you have, you choose not only the test you're going to use, but you also choose the statistic, the central tendency, and the dispersion parameters you're going to use to describe your data. So this is what we call the distribution issue, the probability distribution. So distribution of your data will decide on statistical method and about how you are going to show the basic information about your data. So the graph here, it's in Croatian. It's salary. It's a monthly salary in Croatia by percentage. This is information from National Bureau of Statistics, and you see that approximately 3% of people had less than 3,000 kuna, then 3,000 to 3,200, and so on and so on. So there are actually classes, categories, as you can see, and you can see the percentage of people in each category. Again, by taking just a quick look at this, you can see that this is not normally distributed. And since this is not normally distributed, then it's not appropriate to use mean and standard deviation. You should describe this data with median and interquartile range, which we are going to discuss now. So the data from the National Bureau of Statistics, and this is the same data, but from Ministry of Finance of the Republic of Croatia. You see that this looks even stranger because it's got many more categories. And the first At the first glance, you see the problem. One of the problems with this chart is that the first category is 500 kunas wide. The second one is 300 kunas. Third one is 200. The fourth one is 307 with 369 kunas actually, and so on. So the categories are not the same. So it shouldn't. This chart.
Excuse me, there is
Yep.
someone has raised their hand. Can I let them ask? Okay, Vladimir Trajkovsky, I will allow you to talk now. So you can ask your question. Okay.
Yeah.
Here you are. Vladimir, can you hear us? No. Can you unmute yourself? Hello, can you hear us?
Vladimir can ask at any moment in the chat as well.
Yeah, you can write a question in the chat.
Yeah, of course.
Okay, so
you see, again, this is the official document from the Ministry of Finance of Republic of Croatia, and you see really a significant problem. The width of the first category, second, third, fourth, the categories are not the same. However, if you look like this, if you just take a brief look, they give the impression that the width of the categories is the same, which is not true. So this is a major mistake. But what's actually the problem? Actually, the problem is this. Why am I showing you this? Why cannot you just calculate the mean and report the mean salary in the Republic of Croatia? Why do you have to use median if data are not normally distributed? So it's quite simple. This is another example. So these data here are, of course, for the whole Croatia. This data here is, let's say, for 2, 4, 6, 8, 10, 12, 14, 15, for 15 people. So if you calculate the their mean salary, you'll get some value, which let's say it's $53,000. Doesn't really matter. However, if you add one or more outliers, here outliers are people with more than 100,000 kuna salary. So if to this group you add one or more outliers, and you get quite a different information. So outliers and extremely low and extremely high values, if you don't have the normal distribution, is one of the reasons why you need to report median and not mean. On the example of monthly salaries in Croatia, so if you report mean salary, so if you just add up all these people and divide them by their number, you've got almost 7,000 kuna. So it sounds quite all right. However, if you calculate the median is 5,700. So median salary is much lower. I don't have to tell you which number they normally report in the news. So normally, in all the circumstances, it's this one. So it's almost 7,000 kuna. It's perfect. However, median is 5,700, and we don't know what's mod. We don't know the value of mod. As you know, mod is the value occurring most commonly in the data set. For example, mod, if you go to bank and you see what how many people pay for the credits, the interest rate, then the mod will be, I don't know, 3%, because most of the people pay 3%. There are some people who pay 1.5 or 2 or 2.5. There are some people who pay 5%, but mod, the number, the amount the most people are paying in interest rate, for example, is 3%. We don't know from this data of Ministry of Finance, we don't know what's the mod of salaries in the Republic of Croatia. So let's just briefly see how can we then calculate the median? Calculation of the median is actually very simple if you know just the basic definition. I'll just copy these two columns here, and the only thing I'll do, I'll just sort them. So I'll sort verum first, smallest to largest, and then I'll sort control as well. So we did nothing. We didn't change any of data. We just sorted the data from smallest to largest. Median, then we can calculate it here, and then we can check here. So for verum and median for control. So the name of the function is median. Okay. And in this case, again, median here. I'm lacking some decimal places. So we've got median for the first one, for verum, and median for control. What's the median? Median is the value in the middle of a sorted data set. So instead of having this data set with random participants from first to 42nd, when you sort this value and when you select the one in the middle, this is the median. Now, if the one in the middle is, since we have 42 participants, we don't have the middle one. We don't have the middle. If we had 43, then we would have the participant that is exactly in the middle of our sorted set. Here we don't have. So the median is then mean value between these two. So it's 3.5. And median here, as you can see, is 3. So median is nothing else but the central value, but not, you don't calculate the median, you decide on the position of median. So this is the centrally positioned value in the data set. And we can also calculate lower and upper quartiles. So we can have the interquartile values. Let me just show you the exact definition. So the interquartile value range is the range of the middle 50% of scores. So you calculate it. First, you need to divide your data set in 4 parts. So you sort the data set, you divide it in 4 parts. You decide on you calculate the lower percentile, the higher, and then you get the information you need, and then now you'll see what it means exactly. So we'll have we can have it here. I can put it here. So lower quartile and upper quartile. For this here, we'll use a function. Function is this. If you use quartile including or excluding the median itself, we'll use the one including the median. And so I'll just say, okay, from here, please give me a first quartile. And from here, also from the same array, give me the upper one, so it's third. The second quartile is, of course, median. Same thing, I'll repeat the same thing for here. So first quartile and the same thing again, and I'll get the third one. I can increase the decimal number just in case. So what do these numbers actually mean? Is this, as you can see. So this is my lowest value. In our case, this is 1. Highest value is 5. Second quartile is my median. We've seen that it's 3.5 in one group and 3 in the other. And we've got lower and upper quartile dividing the set in 4 equal parts when we sort the set. So implication of this is that 50% of values, of all the values in Verum, are between 2 and 4, but 50% in control are between 2 and 3. 25% of all the participants have the values above 3, and 25% of all the participants in this group have the value above 4, and also 25% have the value below 2 in, as you can see, both groups. So we've described the data set. This still seems better. So we decided that based on distribution of our data, we cannot use, I mean, it's not completely right to use means and standard deviation. Instead, we should use medians and interquartile range, what we have done here, as you can see. And our treatment Verum still looks better than control. However, we want to know, again, is this just by chance, or is this something actually, or is our product actually doing something? So how can we do that? We've gone through distribution. We've explained why we have to report in some cases mean, in some cases median. Of course, you can always report both, but you need to have the information if the distribution of your data was normal. So the people who will read your article, your data, your interpretation of your data will know what values, what statistics they should take into considerations. So this is finally the questions, and this is why we are here today. We want to know the differences between treatments, result of a chance, and if not, how not, and why not. So this is the other kind of statistics we are going to use. As you remember, we mentioned descriptive statistics, meaning that we've just described our data with means, standard deviations, medians, and interquartile range. And now we want to use inferential statistics. So we want to decide something. We want to attain a new knowledge from our data and see, can we infer something about larger population? Can we say what will happen when we apply this product to the market? This is the procedure we use. It looks complicated, but actually it's rather straightforward. As you can see, it has 7 steps, and the only thing, the basic thing, the most important thing actually you need to do is what you want to do. You want to follow these steps, and this is the procedure for using the inferential statistics. So basically for statistical reasoning. And as you can see, the first step we have here is hypothesis. Hypothesis, which is actually a statistical question. Statistical question meaning that we what's the question we want the answer to. So in our case, we want to know if one treatment is Verum is really superior to control, Or more broadly speaking, are there any statistically significant differences between the two treatments? Meaning, can we infer, can we decide something, conclude something about the general population based on the data we have here? So first we have to formulate the hypothesis, and we start always in statistics. When formulating the hypothesis, you start with the null hypothesis, and the null hypothesis, you've got the definition here. Type of hypothesis that proposes that there is no difference. So we won't be testing if the differences between two treatments are, we won't ask our program, our software, our statistical method, is A better than B? We'll say, we assume that the both treatments are the same, that they are comparable. So the null hypothesis, the thing we are starting with, is these two treatments are the same. And this is our null hypothesis. In this case, the product is equivalent to placebo. This is what we say in the beginning. And we ask our software, can you prove this or can you disprove this? Or more specifically, satisfaction of customers based by this scale that we use from 1 to 5, same as in school, does not differ significantly. So customers, people who have used the products, are approximately comparably satisfied in both groups, in Verum group and in placebo group. You are probably familiar with type 2 and type 1 errors in statistics, but just briefly, if I have the different outcomes, if I have the different outcomes, 4 possible different outcomes if I test the null hypothesis. So the outcomes that I can get testing the null hypothesis, which is there are no differences between treatments. So this is the null hypothesis. The first one, I reject it. And I reject it because it's false. So it's okay. If it's false, I really want to reject it. So I reject the hypothesis because it's false. So perfect, I've done a good job. Alternatively, I can concede it. I can accept it if it's true, which is also fine. So I can reject it when it's false and concede it, accept it when it's true. But I also can do type 1 and type 2 errors, which are actually the opposites. I can reject it when it's true, and I can concede it when it's false. So again, null hypothesis, the results of testing, of asking the statistical question, statistical software, the question about my null hypothesis can be, you should reject it, and this is really so. You should accept it, and in case this is really so, or I can make an error, which can be type 1 or type 2 error. So to cut the long story short, you need to define both type 1 and type 2 errors. So type 1 error, which is known as alpha, which is what's the probability that you will reject the hypothesis if it's true, and type 2 error, which I also define, what's the risk that I will accept the hypothesis when it's false. And of course, 1 minus beta is statistical power, because the statistical power, when I subtract type 2 error from 1, I get the value which tells me what's the probability that I find the difference if it really exists. Okay, so let's see how it looks in my Excel file. So I've got one scores, I've got second set of scores, and I want to know if the differences are between those two scores, between those two groups. If the differences are statistically significant, in other words, should I reject the null hypothesis, which says that differences are actually none or non-existent or quite small. As you know, just a second, as you've seen actually, sorry, let me get back to the PowerPoint. So, as you know from the PowerPoint, the next step is choosing a sample. Choosing the sample is a science in itself. How do you get a representative sample of the population and measure the variable? What we said, since we don't have a time machine, the perfect thing, having a time machine would solve all the statistical problems, because I can take the drug today, wait for 3 weeks, see what the drug does, then go back in time, don't take the drug, wait again for 3 weeks and see what happens then. It would be a perfect situation, but we don't have this opportunity, unfortunately. This is why, this is one of the reasons you need the statistics for. And so you need to choose a representative population. You want the population to represent the general population, and you also want the population in one group to be comparable to the population in the other group. So you want to have two comparable populations, preferably different only in the treatment you're applying. You need to see if data we have are normally distributed. We've tested that, as you remember, and the online test said, no, sorry, your data are not equally distributed. And since the data are not equally distributed, then this is a test from link to the test from before. We need to select an appropriate statistical test. So the information we have up to now, we've set null hypothesis, so the treatments are basically equal. We hope that population is sampled adequately. We've seen that data are not normally distributed, and now we have to choose the appropriate statistical test. Now, what's the statistical test we use when data are not normally distributed? You just, what you need to do, you need to get familiarized with any of the forms, any of the schemes I've shown in the beginning. So if we have normally distributed data, if we had normally, which we don't have, we would use this test, because can you use a parametric test? In other words, is data normally distributed? Is this correlation or no? Was an independent groups design used? Yes, because we had two independent groups, and this is the test I use. In any other situation, no, 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 and this is the test we should use, because we cannot use parametric test, and we answered the same the questions on this side of the graph. So the adequate test we should use is this one. However, the problem in Microsoft Excel is that we don't have this. We don't have Microsoft Excel doesn't have this test included. So instead, I'll do t-test, students t-test here, and then I'll do the Mann-Whitney test in another piece of software. So we'll see what's the difference. Okay, so students t-test. This is the name of the function in Microsoft Excel. So it's t.test, first group, second group. I want two-tailed test, meaning that I want to allow that control is better than verum and that verum is better than control. I don't imply the course of the results, and I also I'll use sample equal variance with equal just a second, with equal variance, and equal variance meaning that I have comparable standard deviations here, as you can see. So I'll use option 2. What does it mean? This is one of the predispositions you need to have to be able to use t-test. So in our case, we have comparable variances, comparable standard deviations, since standard deviation is actually a square root of variance. So we've got comparable variances or standard deviations. We have some means that we want to test, and let's see what the test says. It says p-value is 0.126. Now, what does this mean? What does the infamous p-value means? As you know, we normally set the p we normally set just a second. We normally set the threshold for the significance level against which we compare the p-value. So we normally set it at 0.05, meaning that we allow that in 0.05 or 5% or 1 in 20 situations, we will do this kind of error. So 0.05 alpha of 0.05 means that we will, in approximately 5%, or that we accept the risk that in 5% of all the cases, we will reject the null hypothesis when it's actually true. So this is the threshold that we leave here. What does it mean when I compare it against the p-value I got against the p-value I got here, which is 0.126? Since 0.126 is high, actually not that high, but is much higher than 0.05, I decided I must accept the null hypothesis, meaning that tests, that treatments are actually comparable, and that there is a high probability that this difference can be just a coincidence, or it can be here by chance. So this value, in case this value was, for example, 0.5, so if, for example, it would be below 0.05, 0.05, then I would decide the opposite. I would then have to reject the null hypothesis, and I would say, okay, the differences between treatments are statistically significant, meaning that we expect to see them in general population as well, meaning that we can infer about general population based on the information on the data we have here. And then the conclusion would be quite different. So in the end, we got this. However, you remember that we said that we cannot use, actually, that this is not the right test to use, that we need to use actually another test. So just quickly, continue. I'll open another program so you can see, because in Microsoft Excel we don't have the appropriate methodology. So the problem we have, data are not normally distributed. So this is the problem. The solution is we should use non-parametric test, which is called Mann-Whitney U test, to compare two groups to see if the differences are statistically significant. And the conclusion, but unfortunately we don't have it here. So what we can do, we can use another software which has this option. I'll use standard software we use in teaching here at School of Medicine. So this is Statistica. We could also use SPSS, but we can use this one as well. I'll just quickly copy and paste the data. Generally speaking, all the statistical softwares don't work so that they compare columns, but you need to recode the data in a bit different way. So I'll just add cases, another 42 cases after, and I know that this one is Verum. And this here is control. This is how I copied it from Microsoft Excel. Now we can double check it. If you remember, in Microsoft Excel, we got when using students t-test, we got a value of 0.126. So let's see if we get the same value in Statistica. So statistics basics by groups. I group it by variable too. I can change the names of the variables. So these are the scores. And these here are treatments. Okay, so I can use the test, grouping by treatment and testing by score. Summary, and I get 0.126, so it's the same value. Now, what we want to do, we want to test if what p-value we get when we use the test that is actually appropriate, since data are not normally distributed. So statistics, non-parametrics. So we said the name of the tests is Mann-Whitney. You see it here. The grouping variable is always the same, and this is the outcome. So okay, Mann-Whitney test, and look at this. So p-value is 0.139. So the conclusion could be that all this story was because of this tiny difference between 0.126 and 0.139. However, what's the important part of this? You should always test for the normality of distribution, and when testing for normality of distribution, you should always use the appropriate test. However, if you have a relatively speaking larger sample sizes, such as this one is here, containing 84 subjects, the values of these parametric and non-parametric tests they tend to be quite similar. They're not the same, as you can see, but they tend to be similar. So the larger the group, the lesser the need to use the non-parametric test. But if you have only 5 people, if you have a smaller number of measurements, smaller number of participants, then non-parametric test is of absolute essence, and then you see great differences in statistical reasoning when using non-parametric or parametric tests. And so to conclude with this, so in the end, what we've got we've spent a ton of money. We've got the first group, which had a bit better results in overall satisfaction. We've got a second group, which had a bit lower results, but not quite. And both statistical tests tell us that we need to accept the null hypothesis, and the null hypothesis being that there are no differences between groups, that there is a relatively low probability that the differences between groups are because of the treatment. So we've spent a ton of money and we still got nothing. So what do you do then? So let me show you what you do. You take this, copy, and what you say, so this is Verum group. And now what you can do, you say that this is this is I don't know, so this is what you do, and then you, instead of reporting means or medians, because there is a slight difference, but difference is not statistically significant, so you cannot infer anything about general population. So instead of reporting means or medians, because you cannot do anything with means or medians, you report, just a second, you report share, okay. You want to report this, your groups. However, it still doesn't look very good. So you do another acrobacy and you say these two are when you do in the end, what you do in the end, you sum these three scores, you sum these two scores, and you report that almost more than 3/5 or almost 2/3 of all the participants reported the treatment as good, very good, or excellent, because you didn't get anything here. So you can see how long this process is and what all the things you need to do, all the things you need to consider to decide that there is nothing you have actually here. And this is, again, this is a real world data. This is not randomly generated. And this is, in the end, these are the results the marketing department has used to promote the product. So on the billboard in the ad, you'll see that 62% of participants decided that the treatment is good, very good, or excellent, and based on the fact that you absolutely got nothing here. So this is one case I wanted to show you, and my approach was today to discuss a relatively small small data set to introduce quite a few terms and concepts, and I hope it wasn't too much for you. Since it's we've got less than 20 minutes left, I'm here for any questions you might have. And thank you for your attention.
Thank you very much for this. This was really interesting. I think it's a lot of information to process. So is this this example that you gave, is this data manipulation in a good or in a bad way?
This is absolutely preposterous. This is tragic. This is tragic what they do, and I just always read the small print. Yeah. You absolutely you need to read the small print, especially on billboards. You know, I'm the guy who stops with the car along the edge of the streets and goes and reads what it says, and then I write it down. Oh, you have a sample size of 17 people. Well, good for you. You know, stuff like that. Exactly. But you always get this. You've got 45% of improvement in this, or 72% of that, which is absolutely without any meaning. Yeah.
Yeah, absolutely. There is one good question in Q&As. The question is, what is the minimal number of participants or results for statistical tests to be valid?
Okay, so in statistics, there are different kinds of jobs you can do in statistical analysis. One of the jobs you can do is sample size calculation, sample size analysis, power analysis, as Tatiana has remarked. And the power analysis is actually, it's quite simple. I normally do it by, just give me a second, let me find, it will really take, I'll be just, let me just find it in, I want to show you online how it's actually done. There are a number of the free softwares. G-Power is the best one. I like G-Power. Actually, you install it in Windows. It's open source, it's free, and it's absolutely reliable. But you've got a number of online tests as well. Let me just find it. Okay, a minute. Probability, no. Here it is. Okay, I'll share the screen now with you. Okay. So this is the software, and the question was what's the power analysis? So the power analysis you can do it from different standpoints. You can do what's called the post hoc power analysis, meaning what was my actual chance to find the difference, if the difference really existed, or I can say the following thing. I can do this. I can go to my back to my Excel and say, okay, I've got mean in the first in the variant group of 3.14, in the second group 2.69, and with these standard deviations. Now, if my treatment does something, if the face cream does something, how many people I need to include to prove it, so to lower these versions below 0.05, so I can say statistically significant improvement in something. How many people do I need based on this? In other words, I would consider this to be a pilot study, and then based upon this study, I can decide how many people do I actually need. So let's go back to the software. So in the first group, I had 3.14. In second group, I have 2.69. 1.46 was standard deviation in the first group, 1.22 in the second. Allocation ratio means do I want to have one patient in one group for one, subject? Do I want to have similar, identical groups in the number of participants? So 100 in this, 100 in that, or I can change the allocation number. You may change the allocation number if there are ethical issues. If you're testing a new drug and you don't want to give it to everyone because you suspect there are side effects, then you can have an asymmetrical allocation. We don't need this. Alpha, you remember alpha. So this is type error, type 1 error, meaning what's the probability that will reject the null hypothesis if it's true, and power, what's the probability that will find the difference if it's really there. Okay, calculate. And I get the sample size for group 1 is 140, and the total sample size is 280. So based on the data we have here, if we include approximately 300 people, we would probably see statistical significance, meaning that would be enough for us to conclude that this is really statistically significant, that the difference is significant. Why is this sample size so great? Because the differences between groups are relatively small. When you have great differences between groups, you can more pronounced. You can have a much smaller sample size. And finally, if I increase power from 80, say 95, if I want to be 95% certain that I'll find the difference, if the difference is really there, then the sample size will grow even further. So it will be 462 then. And remember, we had only 84 people. So 84 people are quite enough for a pilot study, but based on that, we cannot conclude about the effect.
Okay, thanks very much for clarifying this. There is one more question in the chat. I just lost it, so let me find it a second. We have a little time, so let's try to answer. Question is regarding using Spearman's and Pearson's correlation coefficient when dealing with small data set of environmental data, less than 20 data points. If I understand correctly, Spearman's
should be used when data is non-normalization, and the opposite for Pearson. Correct. How is the number of less? Well, it's a good point. So I've got a number of data sets. So let me just show you what you've been. Let's just demonstrate what the question was. So I'll close this one. I don't need it anymore. And I'll open, give me a second. So this is height dataset. I've got two variables here, H1 and H2. So this is the height of mothers, and this is the height of their daughters in centimeters. And the question now is, what's the correlation? The easiest way to find the correlation is this. Insert, and I do a scatter plot. So I see if there is a correlation. Of course, since I don't have people of such, so this is okay. Then I add a trend line to see what happens, and I see the higher the mother was, the higher the daughter is. So okay, this is statistically significant, but this is really nothing new.
Mhm.
I can display equation and r squared, meaning this is the simple equation that I can use to calculate if I know the height of the mother x, but based on this this equation, I can calculate the height of the daughter, not just for the heights of mother I have here, but for any value here. And I have r, which r squared, which explains what proportion of the height of the daughters can be explained by the height of the mothers. What you have asked before is, if I have this data, this is 30 data points, okay? But if I have this data here, should I do Spearman's correlation instead of this one? And I'll use the same window I have already opened before. So I'll share my window in statistics here. Okay, this is height. So 30 data points. And what I want to do, I want to test it. I can also use the online program from before. I can test it here, or I can use the software we've shown earlier. Give me a second, just it's a bit, I suppose it's a bit easier to show. So you remember this one from before, when I copy paste the data here, your data is not normally distributed. If I use, however, what I'm also interested in, and this is why we've opened the software, the data set here, this is why you need a more professionally oriented piece of software, because you also want to check for things like this. You want to see descriptives for height, and then I can see how far from normal distribution this is. Generally speaking, any discrepancies from normal distribution should point you to the non-parametric, in this situation, Spearman correlation, and it absolutely makes sense to do with 20 pieces of data with 20 cases. You can do it with 5 cases. It's absolutely no problem. What you want to do after this, you want to calculate your post hoc power to see what's the weight of the conclusions you have reached by your your statistical analysis. So perhaps the most important thing, give me a second just. So absolutely, this is the example with tossing a coin and so on. We don't have a time for this. So pero.hrabač@mef.hr, absolutely feel free to contact me for anything, and you of course have the recording, and I have quite a few additional recordings delving deeper in different statistical methods. So anything you need, I'll be absolutely glad to help you. And I cannot explain you enough how different this all looks when we are live somewhere in the classroom. This is so frustrating, you know, talking into the screen. The thing I like the most, actually, when having presentations like this, is when people interrupt me and to tell me, we don't understand anything, this is rubbish, please again. Now I don't have this feedback.
You don't have the feedback. What?
Yeah.
From the comments in the chat, I would say that people enjoyed it and liked it. It was interesting. Yeah.
They're most kind. Yeah.
From the questions, I would say they did follow and understand most what you were talking about. Thank you so much for joining us here.
Thank you for having me today.
And I'm sure we'll have some more questions for you, and
absolutely,
you can touch and ask for help and assistance, advice, anything. Yeah.
Thank you for having me.
Thank you. Bye. Thanks. Okay, that was it from our statistics workshop, which was from what I can see from your comments in the chat section, very interesting. Right now we will take a few minutes break before we move on to our next workshop, which is also very interesting because it will try to explain how to use tools to organize references in your papers and presentations when you write them. So just a short break for now.